Okay, so welcome everyone to today's colloquium. And the speaker is Dr. Deepak Karan, and he earned his PhD from the Physical Research Laboratory in India in 2018. And his thesis focused on the daytime thermosphere wave dynamics using optical day-glow measurements, which resulted in 5 research articles when he was a PhD student. And he has received the IAGA Young Scientist Award for this work. And in 2019, he came to Boulder and joined CU LASP as a research scientist, and has been a member of NASA's Gold mission team. And his primary research here has focused on using Gold's nighttime data to investigate the ionosphere and plasma processes. And so that's what he will talk about today, and which is on the insights into equatorial ionization anomaly and equatorial plasma bubbles from the Gold mission. So go ahead.
Okay, thanks, Nick. Good afternoon, everyone. Am I audible? People online, can you hear me? Okay.
Yes, we can hear you fine.
Okay, thanks. So, thanks everyone coming here and giving me the opportunity actually to come here and giving this presentation. So, first, before starting the presentation, I would like to make if you have any question or you have any doubt, you can stop me in between, and I'll be happy to take the questions in between. But if you prefer asking at the end, that is okay. So I am working with the Gold's nighttime observation, and the two topics, one is equatorial ionization anomaly, the other is the equatorial plasma bubbles. These are the two ionospheric features, the ionospheric processes that is happening. So I will focus on these two aspects. I am assuming some people know about these two things, and some people, maybe these two topics are completely new to some people. So let me start with some basic about EIA, which is the equatorial ionization anomaly first. So what happens is that if you look at the magnetic field configuration of the Earth, above the geomagnetic equator, the Earth's magnetic fields are completely horizontal. So during the daytime in the E region, there is an eastward electric field. So when that eastward electric field crosses with the northward magnetic field, there is an E cross B of drift, the vertical drift. And that drift, because of that E cross B vertical drift, the plasma gradually moves up. And as it is moving up, it follows the magnetic field lines because of the pressure and gravity, and it starts falling down to either side of the geomagnetic equator. So that cartoon is shown here. This is the geomagnetic equator, this location, and because of the drift, the plasmas are moving up and following either side. And in an animation, let's see how does that look like. Oh, what happened? Before. Okay, there. So this is the geomagnetic. This is the geomagnetic equator here, and these are the magnetic field lines. These lines are the magnetic field lines. The plasma is going up because of the E cross B drift, and as they are going up, they are also following the magnetic field lines to either side of the geomagnetic equator. And okay, so now this is the ionosphere here. This is the air glow that we see in the red and the green. And as the plasma are going to either side of the geomagnetic equator, we will see that they are accumulating on either side of the magnetic equator, making a more electron density. This is if we'll take a latitudinal cut of the electron density, we will see one peak on the north side of the magnetic equator and another peak on the south side of the magnetic equator. So this is generally called as the north crest of EIA, and this is the south crest of the EIA. And at the center is basically the geomagnetic equator. So this is more of like a modeling. So we see more symmetry. This happens. This is formed during the daytime, but it can persist to after the sunset till the nighttime. So it depends upon, as I told, it depends upon the electric field, and the electric field is produced because of the zonal wind in the daytime. So the how is the ionospheric zonal wind, how is the electric field, and how is the conductivity, the net electron density. These are the main contributing factors for the morphology of the EIA. That means at what latitude this north crest will be, at what latitude this south crest will be, and how much will be its electron density. So these are, when I say morphology, that means their latitude location and their electron density, how much dense it can be. So it depends upon many factors. So that is mostly a background about the EIA. Let me go to the EPV, which is called the equatorial plasma bubbles. So what is plasma bubbles? Just after the sunset in the in the ionosphere, what happens that at the bottom of the ionosphere, this is more of like molecular ions are there. So they recombine very faster than the atomic species, which are at the higher like F region altitude. So what happens after the sunset, a less electron density region is at the bottom, and a higher electron density region is sitting at the top. That is kind of an unstable situation when a heavier liquid is sitting on a lighter liquid, so which is kind of called the RT instability, relative instability. So in the ionosphere, now I'm talking about the electron density. So any kind of perturbation in the lower part of that unstable medium, that means at the bottom layer of the E region, if any kind of perturbation because of the wave dynamics or some in situ generated mechanism, so that will trigger some kind of instabilities, and gradually it tries to move up. That you can see in this left side panel. So this is the lighter at the bottom and the heavier at the top, and some disturbance is happening here. It triggers as a kind of like a bubble, basically less electron density inside this region. I always try to imagine this as if I'm going inside a pool and going inside the swimming pool and trying to just blow some air, and gradually it will rise up and it will expand. That kind of thing, analogy comes in my mind. So what happens that initially the electron density profile, if you look at along with the altitude, there will be very clear, smooth pattern of the electron density. But because of this perturbation, when this perturbation is trying to move up, it is going to disturb all the electron density pattern. So in this figure, they are showing some kind of these dense black spots here. So we are seeing that the electron density profile are getting disturbed. And if we have a radar at the bottom on the surface ground, and we are getting the reflective, like the reflected beam, it shows us some disturbances in the ionosphere. And this is way back in 1980s, the initial days of observation of this kind of irregularities. This track is the satellite AE, Atmospheric Explorer Satellite E. When it was passing through that region, we see a lot of like irregularities inside that region. That means the atmospheric electron density pattern is disturbed. So it depends which technique you are using and how you are measuring. You can see that irregularities in different ways. For example, there is ground-based ionosonde, which are the digisonde. People when they're measuring the digisonde, what they do is they're sending some radio wave up in the ionosphere, and they're getting the reflected back that radio wave. And in that signal, it will appear as a spread F. Spread F is the terminology they use. And in the radar and GPS, the terminologies are the scintillations and plumes. And satellite, bytouts, depletions, bubbles, these are basically different terminologies, but the same process. I will say it is the plasma irregularities. That means the ion densities, electron densities are disturbed there. Okay, so I always try to give this information that why we need to study this EIA and EPVs, because the EIA and EPVs are the ionospheric processes which are associated with the electron density, and those are responsible for the radio wave propagation. So any kind of irregularities, any kind of disturbance happened in that medium is definitely going to affect trans-ionospheric radio wave propagation. And we know that we depend like a lot for those trans-ionospheric radio wave propagation. So that is the reason why
Sorry, quick question.
Yeah.
So what's how is radio wavelength compared to the bubble size?
Oh, the bubble size can be like from a kilometer scale, even goes to like hundreds of kilometers.
Mm.
It depends. Like, if those plasma bubbles can be really bigger, but those can be opaque to the radio wave propagation. But at the edge of, this is more like technical now I'm going. So at the edge of the plasma bubble, there can be very small irregularities, very small scale size of irregularities, which is comparable to the radio wavelength.
I see.
So that can produce scintillations there.
Okay, so the irregularity size could be comparable to the radio wavelength.
Right.
I see.
Yeah.
Thank you.
So that is the importance why we need to understand this EIA and EPVs. And if we can really forecast these plasma irregularities, I'm writing here plasma bubbles, but I am using the word irregularities because I want to give you a feeling that these are really very disjoint structures. It is not just like, these are some processes which need not to be taken as granted, because these can affect our socioeconomic input status of a country or the nation. Okay, so I believe I have given you some ideas, some basic information about what is EIA, what is EPV, and why we need to investigate this. And when I told that the prediction, the forecasting of these irregularities needs to be understood, yes, there have been some work, and recently also people are working in our community globally to forecast these plasma bubbles. So we have a basic understanding about the EIA and EPVs. Now, if you see the title of my talk, I have told that something unknown, unseen that has been revealed from the gold. So let us first see those EIA things. So this is an image from the gold. I'll come in a bit about gold satellite, but I think it is an image from a geostationary orbit. So we can see that this green line is the geomagnetic equator, and the bright patch on the north and south are the north crest and south crest of the EIA, which looks really symmetric here. And these structures, these depleted structures perpendicular to the geomagnetic equator, are basically the plasma bubbles. So why these are according to the the formation mechanism, when these depleted region gradually moves up, they follow the magnetic field lines, because this is the movement of the plasma. That's why this structure, their shape should be along the magnetic field lines, because of the, if you draw a perpendicular line to the geomagnetic equator, that will be basically the magnetic field line orientation here. So these are perpendicular to this geomagnetic equator here. But if you come here, the orientation can be different.
Electron density, right?
These are basically the electron density. Think of that way.
Yeah, and which latitude are integrated along the altitude?
I'll comment in my next slide. Yeah. Okay. So little bit about the GOLD mission. It is a spectrograph which is at a geostationary orbit and at minus 47.5 degree west. Basically, this red point is the sub-satellite location of the GOLD, and its field of view is shown by this this area inside this, and this blue on the left and blue on the right are basically the limb of the GOLD observation, and this is the disk. And it takes daytime observation, nighttime observation, it does occultation, and it also takes, from the data we are obtaining the temperature profile, O2 N2, the compositional thermospheric compositions. But in my talk, I am only focusing on the nighttime emissions, what GOLD is measuring. So just give a very brief idea about the GOLD's observation sequence in the nighttime. This is the sunset terminator here. So GOLD starts its observation a little bit after the sunset, and basically 1 hour in local time, it is 1 hour after the sunset, and it goes gradually towards the east side. So this is one image, and this is it takes one image. After 15 minutes, it takes another image in the southern hemisphere. So it takes alternatively from either hemisphere. And also GOLD has dual channel. One is channel A and channel B. Sometimes those channels, channel B does north, south. Again, sometimes we operate both channels together, gradually moving towards the west. So you will see in this animation on the right hand side. But before that, what gold is measuring is 135.6 nanometer emission. That question you asked me, what is it measuring? It is basically the 1356 nanometer is because of the radiative recombination of the electrons and ions. So this emission will peak at the peak a flare altitude where the electron density and ion density is maximum. So that is the basically 1356 is a proxy to the electron density, is a directly square of the electron density. So okay, let me show you here one. It is taking gradually. This red line is the sunset terminator here, and as the sunset terminator is moving towards the west, you see the starting longitude of the image is gradually moving towards the west. Basically, we are following the sunset terminator, and the total width of the image is also gradually increasing because we are getting more area to scan in the night side. So it started from the African longitude sector. Gradually, it is going towards the Atlantic, then towards the South American longitude sector. So this sequence has changed in goals, like 5 years of observation. Sometimes we have done, as I told, both channels together, sometimes just one channel alternatively. But the thing is, at a particular longitude, it's scanned multiple times. That means, like from this image, I can calculate, I can obtain where is the EIA crest location. Like here, you can see that the EIA crest, south crest is here. And at a particular location, its location can be obtained multiple times. So we can take that into advantage in future. And okay, so this is a different day, but in a different color scale, where you see more plasma bubbles on this day, on this night. There are many plasma bubbles here. So my point to show here is that day-to-day variation of the EIA and plasma bubbles happen in gold images. Okay, so this is the basic thing. Let me go. I will talk few new findings from the gold. First, I will share some of the findings regarding the EIA. So on the left-hand side, I am showing four scans. They are just put in this image. So one here, another here. These are 4 images. I have just this is a composite image. So what you are seeing here is that over the South America, you see 2 crests. They're well separated, well bright. That's good, like a geomagnetically quiet time behavior. But what is happening here? It is kind of showing not that much clear variation. So what we did is that we took all the images and obtained the EIA crests, which are shown here. Plus, basically, is the crest location. And these areas, these some plus here as basically the spurious data points. But on this night, if we want to obtain the EIA crest location, basically this is how the EIA crest location, the north crest and south crest are going. Okay, so this is in geomagnetic coordinate system. That's why we see that this is showing some symmetric, and this 0 is the geomagnetic equator here. And in my plot, mostly I will show the geographic longitude and geomagnetic longitude together. Okay, so thus, as I just showed in the previous image, following the similar pattern, we have calculated the EIA crest latitude in the like north crest and the south crest in 3 different seasons. One is the September, December, and March. And x-axis is the longitude, y-axis is the latitude. Look at the red dots. The red dots basically shows the north crest of the EIA. And this cross blue, this is the absolute of the south crest. So south crest should be -5 or -20, whatever, but it is the absolute. That's why we are seeing it is in the positive, and the green is the average. So what is the takeaway? Like the first thing you can see, okay, well, with respect, irrespective of the seasons, in each season, there is a longitudinal variation. First thing. Second thing, whatever is the longitudinal variation, it is changes from season to season. From equinox to solstice, it changes. So previously, I mean, before gold observation, there was some understanding from the low Earth orbiting satellite, from the ground all sky measurements. In the community, we have a fairly good understanding about the seasonal variation and the day-to-day variation. But over the ocean, basically the ocean is, this is the Atlantic Ocean over here. There are very few measurements from only the LEO satellites. So this kind of continuous longitudinal variation picture was not observed before gold. So gold has the advantage there. So when we observe this kind of longitudinal variation, we try to understand why it is happening, what is the process. And with previous understanding, one very insightful observation, what we have found is shown here. The left side is basically the December, the north crest is the red and the south crest is the blue. And on the right hand side, I have taken one image from the December. This is the sunset terminator. Basically, the sunset terminator will be somewhere here. And in December, the subsolar point goes somewhere in the southern hemisphere around -20 degree or -23 degree southern geographic latitude. So now, because of the subsolar point sitting on the southern hemisphere, we expect more ionization there. And at the beginning, when I told you the EIA formation, basically the E cross B drift happens above the geomagnetic equator and it pumps more plasma to either side. Now think of a process which is happening at the equator, it is pumping up, moving more plasma to either side. But because of December, there is more ionization on the southern hemisphere itself. There is a background more production. That's why we are seeing that the southern crest, that the blue is going further away over this, particularly here on the Antarctic and the African sector, where the geomagnetic equator is really further away from the subsolar point. We are seeing the southern crest is further away from the geomagnetic equator, and the north crest is close to the geomagnetic equator. So this kind of seasonal variation, the longitudinal variation and its seasonal pattern is explained more detail in that paper. And but here I'm not going to go all in detail, but what I'm going to say is that the subsolar point dependence on the EIA crest location was not known before, but these observations triggered us, and the investigation we found that. Okay, this is one. The second thing is X pattern merging of the EIA. This is like if you have been in the CEDAR or like sometimes in ASU, this is a popular topic at the moment. So the X pattern merging in the EIA, what it means is that sometimes due to some reason, both the north crest and the south crest, they are coming really close to each other, and it appears as if they are crossing to each other. Back in for the first time back in 1972, when the Apollo mission was there, from the ultraviolet camera on the surface of the moon, this image was taken, and we see because of the orientation, there was not like a continuous measurements, but it is a snap one-day measurement. We see the north crest and south crest, they were just touching it. They reported it is kind of a lambda structure, and until now there was nothing. But what happened when gold started its observation, there have been 3 publications. One was during the Tonga volcanic eruption, and one was for a geomagnetic activity, like the geomagnetic storm. It was observed that the EIA crests are crossing with each other, that forming an X type of pattern. And this is during the Tonga volcanic eruption, and it was observed that at this longitude, because of the westward wind, the vertical drift was downward. So because of when I told the EIA formation, the electric field should be eastward, and the northward magnetic field creates a vertical upward drift. But during this case, the wind was reversal. That means the wind was westward, and the electric field was downward that time. Sorry, the vertical drift was downward. That because of which the EIA started collapsing. This is what they attributed for the Tonga volcanic eruption. And there was a geomagnetically active period, and for that case, here you see both the crests, the north over South America, this is well separated, but over Atlantic, these are merged, and these are merged over a wider longitude. So this is extended merging of the EIA crest. And in this paper, they attributed it because of the distance dynamo effect, which is basically making this kind of structure. But recently, Laskar et al., they showed that, hey, it is not just the geomagnetic disturbance or any kind of special occasion, when this kind of thing, the EIA X pattern is happening. It can also happen like a completely geomagnetically quiet time. So what could be the reason? In that paper, they looked at the simulations, the Wakamak simulations, and they found that the vertical drift, which was supposed to be in the daytime, which is supposed to be upward in the daytime, in some cases it is downward. And whenever it is downward, before the sunset, whenever the vertical drift is downward, that time you will see the EIA crest will start collapsing and you will see X pattern. And Laskar et al. In their model simulation, they found that this X pattern, not only it can start during the pre-sunset condition and it will persist after the sunset. So these kind of observations, like more dynamics of the EIA crests, have been observed from the gold observations. Okay. Those are the geomagnetically quiet time things. Now let us go to the geomagnetically storm time. What happens during geomagnetically storm? When you give a talk at HAO, you expect like more experts from like the solar background. Okay, and if you bring any kind of solar storm, first thing is they will like, okay, so what is happening inside the sun? But I am not really going that far. I will show that impact on the ionosphere. Okay, so first thing I will show what is happening during, we have observed 3 cases. One was 2020 September 27 geomagnetic storm. I mean, you are the expert here, but if I will just say that it is a CIR kind of storm, I think that will be sufficient enough from the solar wind speed, IMFBG. We can see that during this time it was kind of a CIR kind of storm, and we observed this from 268 to 272. These are the days, and look at these blue lines. These blue lines corresponds to the time when gold does its nighttime observation. So particularly on this evening, 271, on this evening, this is 270, this is 271 here. On this evening, when there is a sudden drop in the CMH index and sudden rise in the solar wind temperature and the speed, and here IMFBG was turning southward. That is the time which is marked by this vertical dashed line here. And look, gold started its nighttime observation just after that. I mean, I will say it is like a coincidence, or like, yes, it may be a coincidence that when the disturbance happened and you are taking your measurements just after that, perfectly to see what is happening in the ionosphere. We looked at the EIA crest latitudes, and what we observed is that, so we observed, these are the 3 different colors, shows for different days. I have taken 3 different days here, but remember this 271 is that this color. This is the north crest and this is the south crest. What we are seeing is that the north crest has gone poleward on that day, and the south crest has also gone poleward. Here I am not showing the absolute of the south crest. It is the like actual value. That's why it is in negative. So we are seeing that over a wider longitude range, the EIA crests has gone poleward. That means the electric field over the equator is influenced by the solar wind disturbance. That means one of the mechanism is the prompt penetration electric field. This should be like whenever the IMFBG turns negative, that is the time. Just after that, we are seeing this poleward movement of the EIA crest. That what this indicates is that there should be a there should be a real-time penetration of the electric field to the equator, which is the prompt penetration electric field. The important point here is that we are seeing this shift of the EIA crest over 30-degree longitudinal extent here. Like almost, if you look at this longitude, it is almost 30-degree. And let us go to another storm, which happened last year in April 23. And this is a CME kind of storm. And here, this red line shows the gold's observation period, which was going through this phase here. This is the CMH. And during that time, we see that IMFBG has gone, it is going, just before that, it was going in the negative. And we expect its effect in the again in the nighttime ionosphere. And what we observed is shown here. These red points, these are the actual EIA north crests, and the blue is the south crest. I subtracted the quiet time values. This is the quiet time value. This is the quiet, I think 10 to 15 days averaged before the storm. So this is the shift. What we are observing is that at this longitude, around minus 40 degree, minus 10 degree geographic longitude, we see the maximum polar extension of the EIA crests. And it is not happening over a wider longitude range. It is happening over maybe 10 degree longitude range. So there is a difference. It is not that in each storm can produce similar kind of impact on the electric field, and important is at what longitude extent it is affecting the equatorial electric field. So there is a difference. Now your question will be, okay, well, what happened during the Gannon storm? Okay, which happened recently. So this is the Gannon storm, and I'm assuming everybody knows its extent. It is a G5 kind of storm. Let me directly show you these gold images, what we observed. So this is the sunset terminator here, and the north crest here, south crest here. Have a look at this. Well, look at the south crests and north crest. Let me run that again. Yeah. The south crest is going poleward. At some point of time, merging with the aurora, again detaching, again it will merge. This is interesting. When we saw this just the next morning of this storm, we are like, wow, we have never seen this kind of thing before, never ever. Definitely we didn't have measurement. Maybe it would have been there in the past, but since this was not observed, we couldn't really anticipate, okay, sometimes the equatorial process, the EIA, can go all the way to the pole, merge with the aurora, which tells basically there is no mid-latitude ionosphere. So that kind of thing is happening. So these are some snapshots, but we calculated the EIA crest, the north crest and the south crest. Interestingly, we are seeing that the north crest is reaching almost 40 degree geomagnetic latitude, and the south crest is going till 35 degree geomagnetic latitude. This is like way. These are really larger values. The experts who knows about the EIA crest latitudes, they will be really surprised to see this. There is a process called super fountain effect. Sometimes the super fountain effect happens because of the strengthening of the electric field due to some reason, whatever the reason may be. The EIA crest, the pumping can be really hard, and the ionospheric layer can go up, and it will pump the plasma almost during that 2003 or 2000 that Halloween storm. During that time, the magnetic latitudes, the EIA crests reached around minus 28 degree and 28 degree magnetic latitude. But in this case, we are reaching it is reaching till 40 degree magnetic latitude. So we can see how much how much impact the significant impact this storm created in the ionospheric system. And we calculated the movement of the south crests. Since we have multiple observations, we can calculate at what rate it was moving. The speed was around 450 meter per second. To make that 450 meter per second of the velocity, the equatorial electric field, we calculated it was coming around like 10 or something millivolt per meter. Generally, in a quiet time, its value, the equatorial electric field value is around 0.5 or 0.8 millivolt per meter. So that kind of electric field, how it could have been produced. But we looked at the digicent observation over the equator, and we see that the ionospheric layer has gone really high up and to produce this super fountain effect. So these are we have explained these things in the paper. So what this is one additional thing about that storm, that when we are gold observes in 1356, and also it does observation in LBH. So look at this red line, the boundary of the red line. This is the aurora. We see that in 1356, it is touching the South America continent, but not in the LVH. So it tells that the soft electrons, they are reaching towards the low latitudes. So this is a nice observations from the gold. So these are some interesting and new observations about the EIA. Now let me go to the EPB, the plasma bubble thing. Again, the three storm, I will show, just talk about what happened to the plasma bubble observation during those three storms. This is the first storm in September 27, 2020. Here, each cross is basically the occurrence of a plasma bubble. For example, at day, the y-axis is the day of the year. At the day of the year 246, only one plasma bubble was observed over the African longitude sector. And on the next day, there was no bubble. And shows the total number of plasma bubbles on these days. And the blue here is the AP index. And we see that 271, that day of the year, we see more number of plasma bubble occurred during that time. So it tells that this storm supported the occurrence of the plasma bubbles. And also we observed that the EIA crests had gone really further away because of the fountain effect. So this shows the total ionospheric response to that storm. Well, in April 23, 2023, this is interesting. Why it is interesting? I have shown this to all the experts in the plasma bubble, whomever are doing analysis. Because look at the images here. Over the Africa, you see there are some plasma bubbles here. On the same night, when we are taking observation over Atlantic or over the South America, it was completely quiet. There was nothing. And I will show you those plasma bubbles in geomagnetic coordinate system, they look something like this. If you remember, at the beginning, I was telling you that the plasma bubbles should be aligned along the magnetic field lines. But these are not. These are showing a reverse C-shaped kind of structure. We know why this C-shaped structure and the reverse C-shaped structure can happen, but not to this extent. When we calculated this, the westward tilt of the plasma bubble, we found that it was almost the plasma bubble was going beyond 36-degree magnetic latitude, but their westward tilt almost 50 degree with respect to the magnetic field lines. So that kind of that extent of westward tilt were not observed before. Then we thought, okay, let us see how the plasma bubble is moving. So for that, we did some kind of chaogram, and this is the chaogram at the south EIA crest. This is at the equator. This is at the north EIA crest. Without going in detail, what I can say is that the plasma bubbles, these bubbles, were moving eastward at the equator, and at the north crest and south crests, these were moving westward. So basically, when you were going away from the equator, at some point of time, there should be a reversal from eastward to westward. So how can we calculate that? We can take small latitudinal range and calculate the drift speed. Then you can see where the reversal is happening. And we did that, and we found that around plus minus 20 degree magnetic latitude, that reversal from eastward to westward happened. And looking at the magnetic field configuration of the Earth, if the 20 degree magnetic field line, it should correspond to certain apex altitude. 15 degree magnetic latitude should correspond to another latitude, another altitude. That means when we are calculating the drifts at different latitudes, that is basically giving us the information about the altitudinal variation of the zonal wind at the equator. So we obtained, by doing that analogy, we obtained the zonal drift at different apex altitude. And what we found is that as we are going to the higher apex altitude till 1500 kilometer, the zonal drift was following certain trend. And after that, the slope is completely different. Okay, so in literature, and so far we were thinking, okay, as we are going up, it may follow a linear trend. But this particular event is telling us that, hey, no, it can break at certain point of altitude above which it is moving like in a different way. So this kind of information regarding the velocity gradient along the altitudinal direction was not reported before, or because to do this we need to observe the complete plasma bubble morphology from the south to the north. So that is the uniqueness of the gold observations, I'll say. And yeah.
So when we talk about the EPB zometry, are you referring to the motion of the bubble itself, or
Yeah.
just the inside of the bubble?
No, it is the bulk motion of the like whole plasma bubble.
Okay.
And during the Gannon storm, and we see that there were some plasma. You see there are plasma bubbles here, and also we see when the EIA crests reached over this, here we see some structures in the plasma bubbles. That means here also you can see this structure here, but its northern foot point we couldn't find it. Maybe it is inside there, but we didn't do looked into that there. So this Gannon storm also showed some mid-latitude plasma bubbles there. Okay, so these are some interesting findings about the Gannon, the geomagnetic storm. And I am at the last point. This is the last result I will show. The EPB structure in the literature, this is one all sky imager. We see this is showing like this is a straight structure. This is in a this is a low Earth orbiting satellite measurements where the plasma bubbles is a reverse C-shaped structure, and this is modeled by Hubeitel, and where he was showing how the neutral wind can create the reverse C-shaped structure or the C-shaped structure. And this is from gold measurement where we observed very straight field aligned plasma bubbles. And sometimes we are seeing some like a comb kind of structures, very plasma bubbles very close to each other, but oriented either straight or in a singular direction, either C-shape or reverse C-shape structure. Not until this image. These are the two images we observed from the 5.5 years of gold, where one C-shape structure and a reverse C-shape structure are located very close to each other. And there is another case where the reverse C-shape C and the C, they are in the opposite side, but happening very close to each other. The understanding in the literature tells that for the C-shape structure, as at the geomagnetic equator, when you go up, if the neutral wind speed, the zonal wind speed will increase, then that can favor a C-shape structure. But as you are going to higher altitude, if the zonal wind speed will reduce, then that can create a reverse C-shape structure. That is fine. So, but when these C and reverse C, they're happening very close to each other. Think what could have been happened in a very smaller longitudinal difference. It will create a shear kind of in the wind pattern. Is it? If I will not show this image to anyone in our field, and I'll tell them that, hey, here there is a positive gradient in the wind, but if you'll go 5 degrees to the east or west, there will be a negative gradient in the zonal wind. They will not believe me. They'll say, no, it can't be in that small longitudinal range. But when you look at these observations, then how these occurred? What could be the reason? I mean, so I don't have any I don't have any answer to that at the moment. Just I can we can see that I can say that this is a very rare observations, and we reported this, and it is a challenge. I mean, whether it is a neutral wind or electric field, or it is a combination of both, that can create some kind of turbulence in a smaller longitude range. When I when I was writing this paper, that time there was a paper during my PhD time, using the optical day glow measurement emission, I found that the day glow emission pattern, it was showing a difference in the thermospheric wave dynamics in a 5 degree longitude range, and we attributed that probably the electric field is different within 5 degree longitude scale. And now this kind of observation again is making some like a strong point that the either the wind or the electric field definitely shows a small scale variations. But in this table, basically we are showing the drift speed that I told you that at the C-shaped structure at the equator it will move slowly, but at the north crest and south crest it will move faster. So it is okay. You can check this. But now it is a challenge for the numerical simulation that what could be the reason for this. If any kind of structure, if like personally, when I feel in a turbulence that is happening in the ionosphere, that kind of structure, I feel, wow, this can really disturb the whole ionosphere during that time, particularly at that location. So I mean, in my mind, I see catastrophic effect of these kind of structures on the surface of the Earth when your trans-ionospheric wave propagation can completely gone. So this is a very interesting thing. So at the end, I will say that GOLD data has revealed many new insights about the EIA and EPBs. And when in the community we believe, okay, well, we know a lot of things and probably everything about the EIA and EPBs, these observations we're saying, no, there is more into those kind of things, and suitable observations and the suitable technique can give you many insights and some things which probably we have never anticipated that is happening in the nature. So nature is always going far ahead of us. I believe that. So more to explore, and thank you.
Yeah. Are there any questions?
Should I let other people go first?
Yeah, I was asking about the general profile or general behavior of EIA with respect to geomagnetic activity, because the way that the two observation that you have shown, the condition was different. Means particularly if you see for the April 24 storm, the period where the GOLD observations are that the BZ were recovering and the storm was also a small recovery. It was not a single step storm, it was multi-step. And as for the Mother's Day storm, that was typically with the effect of BY, not typically with the BZ. So what's general profile of EIA with respect to geomagnetic activity?
Yeah, I mean, what I believe that it is important whenever the BG or BY is turning positive or negative, during that time, where is the sunset happening on the surface of the Earth? That is crucial. And how much, like, again, along with that, what was the season? Okay, so this is like it is not a direct, but definitely where the sunset was happening and in which season it is happening, because the declination angle and also the geomagnetic configuration, because of the declination angle, that has a very strong effect on the reversal enhancement and the EIA formation. So these are three important factors. So maybe for each storm, this configuration will not be the same. That's why there is no much. It will be different. That is what I understand from these observations at the moment.
Yeah, you mentioned that the downward vertical drift becomes the proxy for EIA.
Yeah.
Like how often it is, and like for the downward shifting.
Yeah. So in Fazlul's paper and Fazlul for the geomagnetic quiet time, he showed that this vertical down drift, but vertical downward drift is happening, and in the model he saw it very often. It was happening.
Okay.
Okay, and in there is a paper which is coming soon where from our team we are making a data log out of all the X patterns. It will be published, and what at the moment we observed that more it was happening during the low solar activity time, and it is happening at the longitude where the geomagnetic and geographic were crossing each other. So these are some primary understanding about. So maybe that is where this downward drift is happening, but not very thorough statistics. We don't have that kind of things at the moment.
Yeah, thank you. I have another question.
Yeah.
Okay. Yeah, like so our last case, like showing the station
Yeah.
plasma bubble and
The
that, like,
reverse is
how-
set together.
right, yeah, how localized it is.
When-
Like, do you think the mechanism is like driving it? How localized it should be?
When you're saying localized, that means you're saying within how much longitude range
Yeah,
it is happening. It was happening over 6-degree longitude range.
and if it's actually, it could be attributed to the zero winds.
Yeah,
Like,
the zonal wind, definitely it should be a wind, but the interesting thing is it should change immediately within 5 degrees. Whatever is happening on the west, it should be completely opposite on the east. That's why we can see because C-shape pattern, the C-shape plasma will happen when the as we are going to higher altitude, zonal wind speed should increase. And the reverse C-shape should happen when we are going to higher altitude and zonal wind speed should decrease. And this kind of structure, when it is like this or like this, that tells that within 5 degrees, this gradient should completely change. And next to that, there is a straight plasma bubble.
yeah,
Immediately, it should stop again. That is what is making it more complex. And I know that the modelers tried to look at on this day, particularly using the Wakamax. Even SAMI 3 and Wakamax combining those two, it couldn't produce these things. They didn't see this. Yeah, so there is more. Something is probably not in my mind. So I always ask that, yeah, can you say something? What do you think could have happened or that kind of thing?
thank you.
Okay, could you go back to the previous slide where you showed the seasonal dependence, the EPB, EIA crest location?
Okay.
I'm not sure if I missed that.
It is
Yeah.
here.
Yeah. So it looks like in the wind solstice, not just as a central location, but also as a separation also larger compared to the equinox, right?
Yeah.
So is that also just can be fully explained by that the subsolar location?
No, the subsolar point is one component to it.
Yeah, that's what I want to.
Yeah, it is not the only component, no. Because the EIA, it depends how much electron density was there in the daytime, basically your background, which is definitely contributed by the solar sunspot, the subsolar point. And then along with that, now what is the wind pattern? What is the meridional wind pattern? And then what is the electric field at the equator? And on the top of that, how is the declination angle there? So all these things are going to contribute for that.
Okay, just to go a little bit further here. So regarding that larger separation, in the middle panel.
This
here.
one.
Yeah. That means it has a larger separation, right?
So, yeah, I think that is why I like particularly this image. This is the geomagnetic equator here. And think this is the subsolar point here. And the fountain effect, it should be symmetric with respect to this geomagnetic equator. And now because of more production here, look at the distance from the geomagnetic equator at this longitude. But when we are going over America, that is not happening. That's why we see more separation between the north and south over these longitude sectors. But when we are going to over the South America, there the subsolar point at the geomagnetic equator are close to each other. That's why we are not seeing much difference in the north and south.
Is this have any relation to the orbit itself of the GOES satellite?
Gold is geostationary orbit, so it is just sitting there and always looking this portion of the Earth. It doesn't look anywhere else. It is like a stationary camera sitting there.
So what if there's another Queen GOES satellite on the other side of the Earth?
Now you're like, oh, let's bring it up. Yeah, that will be really awesome to have like more, at least 2 to 3, and have a global picture continuously. That will be awesome. Yeah, because now whatever all the informations I'm telling, we have obtained only from this site. So it will be interesting to see what is happening in other side of the globe.
So just that, by your theory of this subsolar point, if you look in June solstice,
Yeah,
are they much further apart in over the US?
there is
American
no
segment?
EIA
Okay.
because in the June, what happens? I have that.
I don't think you showed June on the other.
No,
Yeah.
June. Actually, June we don't see any EIA because in the June, what happens? Look at the sunset terminator. This one is the sunset terminator, and this is the basically our declination angle, the perpendicular. These are not going to match, but in December they match to each other. So when the sunset terminator and your magnetic field line, they are matching to each other, that means at the north hemisphere and the south hemisphere, the sunset is happening at the exactly at the same time. And that is more conducive for the strengthening of the pre-reversal enhancement. So that is the role of the declination angle. But in June, now this is the sunset terminator. The if you take in a single magnetic field line, its southern foot point will enter the sunset terminator fast, and the northern will enter later. So that will create a difference and in the F-region dynamo.
So the
So with
nighttime
nighttime.
is quite dependent on the
Yeah, nighttime
reversal
behavior.
enhancements.
Yes, and that is going to do with the orientation of the sunset
Yeah.
terminator and the declination angle. So that's why we didn't look into the June because there was no EIA there.
Or no nighttime EIA.
No nighttime. Yes, I should say this. No nighttime EIA. Yeah, and that also matches with the this this is a Hikamarka vertical.
This I understand.
Yeah. So yeah.
I think Wenbin has a question.
Okay.
No, I just have a comment in there's a annular symmetry in the ionosphere where December solstice have more density, electron density. That's compared to June. June is have the lowest electron temperature, daytime and nighttime. So normally, and in June solstice, the gold won't see EIA, and also that's another consideration here.
Yeah. Yeah, I have seen like with increasing the solar activity, the June in June the EIA is we can see the EIA.
Yeah,
I think
on the maximum we say the
Yeah, it is.
say
I think
the-
again the solar.
on the minimum we cannot see it because
Right.
it's lower. Yeah.
Are there any other questions?
I expect. I think looking at the health of the world, how it is doing, I think it is going to be there for a while. Yeah, more 10 years, I don't know, because there is a limitation in the detector. Okay, how much recover? I mean, when we are observing the 3056, it degrades and also it recovers. So it is happening. So I believe 10 years, I don't know. It is a question to Richard actually.
Yeah, I'm just curious.
Yeah, no, but definitely it is going to be there for
For the kilomax period.
yeah, I think so. Yeah.
Any other questions? Okay, well,
Okay.
thank you again.
Okay, thanks.